We're going to look at how to proceed with a weak acid, strong base titration calculation, or it could be a weak base, strong acid titration calculation. If you get stuck at any point, just remember to look back at this slide in the notes. Because if you're going to find the pH of the solution, you've got to be able to get to the hydrogen ion concentration. So here's what you will do. The first thing you have to do is a stoichiometry problem. You're going to assume that the hydroxide ion from the strong base and the weak acid in the flask are going to react 100%. Now, if you were adding a strong acid to a weak base, you would assume that the hydrogen ion from the strong acid would react with the weak base, and they would react 100%. You're going to determine the concentration of your conjugate acid-base pair, like when we ice our problems. This part is exactly like how we handle the buffer solution stoichiometry calculation. After that, you will have an amount of the acid in its conjugate base, the weak acid in its conjugate base, so you can then use the Henderson-Hasselbalch equation. So in the notes, this is our first example from our book. It says, consider the titration between 50 milliliters of 0.1 molar acetic acid, and I give you the Ka, being titrated with 0.1 molar sodium hydroxide. Wants us to calculate the pH of the solution at each point in the titration. Now, initially in part A, it wants us to calculate the pH before any sodium hydroxide has been added. So remember, your sodium hydroxide in this example is in your burette. Inside your flask, you have your weak acid. In this case, that's acetic acid. So before any sodium hydroxide has been added, the pH in the flask is what we're going to determine. So this is just a weak acid equilibrium calculation. So you want to take your weak acid. This represents the formula for a weak acid. And remember, these are going to dissociate only about 5%. But when they dissociate, they're going to form hydrogen ions and acetate ions. You're going to ice your problem. And in the beginning, there's neither of the ions present, and that you're told in the flask you have 50 milliliters of 0.1 molar acetic acid. So you've got 0.10 molar of acetic acid. Remember, you define your shift in terms of x here because it's a very small shift. So minus x plus x plus x. Anytime you have an initial amount present with these weak acids or weak bases, you can neglect your x here to help simplify our math. That's going to give you 0.1 molar of the acetic acid, and your hydrogen ion and your acetate ion concentration are represented by our x here. These are the values you're going to plug into your law of mass action. So K